Hello, is it audible? My sound is audible? Hello, is this my sound is audible?
Yes, sir.
So we are going to start the session of today. But before we are going to start the session of today, let's build up some platform. Uh, and we just wait for 5 more minutes so other can join us. So we first build up one platform, and then we discuss about the today's experiment. The today experiment is to find the Fourier transform of a given signal. So here it is essential at this junction to understand what is the importance of a Fourier transform and what is that, and how is it helpful, or is it significant to understand the analysis, to understand the things in a communication field, and how we can do some analysis using that one. Okay, so I am sharing my screen with you, and hope this will be visible. Okay, now is it audible and visible? My screen is visible to you. I have written the date on the main screen.
Yes, sir.
Yes, sir, it is visible.
Okay, so now we are going to discuss about the Fourier transform. And in this today's experiment, we will discuss how we will see by using a MATLAB simulations how we can find the Fourier transform of any signal. So first we should learn what is the Fourier transform. So the signal which is in time domain, we have already discussed earlier. If any signal is in a time domain, so this signal is known as a G of t signal. And if we are converting the signal in a frequency domain, then the signal is known of a G of f signal. So the signal which is in time domain, it is known as a G of t signal, and the signal which is in frequency domain, it is known as a G of f signal. And the process to convert the signal from time domain to this frequency domain, this is known as a Fourier transform. So Fourier transform is a tool or method to convert any time domain signal into the frequency domain signal. And if we do the reverse process, if we have the signal G of f and we want to convert in the G of t, means frequency domain signal, if we are going to convert in a time domain, so this process is known as a inverse Fourier transform. Now we simply use this word ft. Ft, it simply means the Fourier transform, and IFT word is used as a shortcut to define is the inverse Fourier transform. Very importantly, we need to understand over here what is the need to convert this time domain signal to frequency domain signal. So there are some hidden aspect which cannot be highlighted in a time domain signal. Like is there are few questions are there. Like is what is the bandwidth of signal? What is the bandwidth of signal? This is a very important questions. uh, it because whenever we are transmitting any signal, so every channel has a band limited channel. I mean, they can transmit only some particular amount of the information. So every signal is to be transmitted with some precise bandwidth limitation, and that's why this bandwidth, we should know about what is the bandwidth of any signal. These questions may not be answered out if we have signals in a time domain, but if we have a signal in this G of f is available, or frequency domain version of the signal is available, then we can answer out this question. So what is the bandwidth of signal? The answer, we need G of f should be available. The first requirement of this one, G of f should be available for this one. And if G of f is available with us, then we can say the signal is starting from some frequency. This is the frequency domain signal, where the this x-axis is a frequency, where in time domain signal the x-axis is a time. Here we can see if any signal is in a time domain like this, so x-axis is a time and y-axis defines the amplitude. But if any signal is in a frequency domain, so here this x-axis is a frequency and this y-axis is defines the amplitude. So this graph will tell us that what is the starting frequency, maybe some frequency here, f1 frequency and f2 frequency. So all the signal, all the components of the signal does lies within the range of frequency f2 to f1. So this is known as a bandwidth of signal, this bandwidth. So bandwidth is simply defined by the highest frequency to the lowest frequency. But if the signal is in a time domain like this one, right, we cannot have any idea about this signal. So if we can convert the signal in frequency domain, then and then this components can be visualized, right? This component, the bandwidth, can be visualized. The another very important concept is energy spectral density. How much energy per frequency component, that is known as the energy spectral density, that can even be visualized if we have a signal in a frequency domain. Then there is one more parameter known as a power spectral density. This power spectral density is also very important parameter. It defines the graph of power versus frequency. Energy spectral density graph defines the energy per frequency. So from energy spectral density, we can identify what is the contribution of individual frequency, individual signal, what is the contribution of signal with individual frequency component in contributing the total energy, where in PSD we can find what is the contribution of individual components of frequency in our total power. So this energy spectral density and power spectral density, they both are very important parameters, and that is even represented in form of a frequency domain. So that is also important. If you want to change some parameters, if you want to remove some components, or if you want to save, if one want to save, if anyone can want to save the frequency spectrum, then again G of F should be available. G of F is required. So it means there are many places in communications where G of F is essential parameters. If we want to find the bandwidth of signals, or we want to find the energy spectral density of signals, if you want to find the power spectral density of signals, or we may want to say, or we want to modify some spectrum components of the signals, then again we need the signals in a frequency domain. We need the presentation of signals should be in frequency domain. But it is not always the case. Most of the times we have a signal available in a time domain. So if you want to see the frequency spectrums that we want to convert the signals in a frequency domain, so this conversions from time to frequency domain is known as a Fourier transformations, and we have a mathematical representation how we can convert this G of T signals into G of F signals. So that we are going to look around. One other important parameters that one other very essential things that I would like to highlight is, if we are changing something here in a time domain, if the signal is changed, if this one is changed in a time domain, so it is reflected here, it is also changed. This frequency spectrum is also changed because both are correlated. Like for example, if we are adding some signal over here, if we are changing some components of then frequency spectrum is also changed. Then if the same in the similar manner, if we made some change over here, then it is also reflected in a time domain, right? So it means if something is changed in a time domain, and then it is reflected in frequency domain. And if something is changed in a frequency domain, some parameters are going to change in a frequency domain, then it is also reflected in a time domain. So both the things are correlated with each other. You can say both the things are the two different side of a coins. Two different side of a coins. One is the time domain, and another is the frequency domain. So if some changes are made in time domain, they are reflected in frequency domain. And inversely, inverse is also true. If some changes are made in frequency domain, they are reflected in a time domain. So both the domains are linked with each other. They are just represent in a different domain, but the all over components and contains, they are correlated in both the domains. So this is very important that you need to understand. Now here we are going to find the Fourier transform of any signal. So we can say, if we find the Fourier transform of any signal is actually a process to convert, this is the process to convert any time domain signal into the frequency domain signal, in the frequency domain signals, or we can find the frequency domain version of the signals from time domain signal. So what is available, we have available the signals is in time domain is available. And what we need to find, we need to find the signals in a frequency domain, that is known as a G of F. So this one is known as a frequency domain signal, and the first one is known as a time domain signal. So if we find this one, that we can have G of F is simply defined as the integration of minus infinity to infinity G of T into e raised to minus j omega t dt. This is the equation to find the frequency domain version of this signal, right? So that is the signal in a time domain. We multiply with the e raised to minus j omega t and integrate the signals over the from minus infinity to plus infinity. And if we find the signals, then we are able to find the signal in a frequency domain. So this both are related with each other. One is in a time domain, another is known as a frequency domain. Now, if you go with the inverse Fourier transform, so in inverse Fourier transform, if we are applying some process on the signals and we are converting the signals in a frequency domain, so then we have a g of f is available in that case. And what to find here is the g of f should be found. So main objective uh, is to find a g of t. So it is totally reverse process than the Fourier transform. In a Fourier transform, we have g of t is available, and we find the g of f. In inverse Fourier transform, we have a g of f is available, and we are going to find the g of t. So that means the frequency domain version of the signal is available, and we are interested to find the time domain version of the signal. This we are interested to find. So that way we can say any signal g of t can be found as a inverse Fourier transform of the g of f. So g of t we are interested to find from the g of f. So that is multiply with e raised to plus j omega t. That is very important. And here we have taken the integration with respect to time, but here we don't have a signals available in a time domain. We have the signals available in a frequency domain. So this integration is taken with respect to the frequency. So that is with df. So these two are very, very important equations. If you want to find the Fourier transform, then we are using this equations. If we have to find this, if we want to find the signal in a time domain, so we have it this equation as available. So we can have g of t is available from g of f, and g of f is available from g of t. So these are the two processes that how we can find the Fourier transform and inverse Fourier transform. Now, one very important thing that we need to note down here is that we need to note down over here is that the Fourier transform is available, or it is possible only for non-periodic signals. So if any signal is periodic in nature, then g of f is does not available. This is very important for a non-periodic signal. So it means g of f exists for non-periodic signal only. Periodic signal. But if your signal is a periodic, then g of f doesn't exist. Then g of f doesn't exist directly means you have a possible indirect way available in which you can find the autocorrelation first, and taking the Fourier transform of autocorrelation we can find the g of f. But indirectly we don't have any way to find the g of f. So g of f doesn't directly exist for periodic signal. This is very, very important integrations. That is, you can note down this one. This is very, very important. G of f exists for a non-periodic signal by the formulas that we have shown, and g of f doesn't exist directly exist by the formula that we have shown for a periodic kind of a signal. Okay, so now we what we do in this experiment. So let's before this, let's understand. We will choose any arbitrary signal. We can choose this arbitrary signals, right? And this signals we will choose as g of t. How we produce? So we are mixing of the two sinusoidal signals with the two different frequency. This one and with another sinusoidal signal, signal number one, that we consider as a g of t signal in a time domain. There is another signals we will consider as a signal g2 of t. There is also in a time domain, and both were added together, and finally we will produce the signal that is a g of t. So g of t is a arbitrary signals which is produced by by adding the two uh, signals g1 of t and g2 of t, right? By adding the two signals g1 of t and g2 of t, and we will find this Fourier transform of this signal. We will find the Fourier transform of, yeah, this is looks like a periodic signal, but if we produce in a MATLAB, so it will be exist for a particular duration, so that becomes a automatically non-periodic signal. So if we find the Fourier transform of this, so we can find some signal like this one, and this is known as a g of f signals with respect to the frequency domain f. And where the signal does lies, so signals may be lies with some frequency to some other frequency, and if it is low pass signal, so there centrally we have a zero frequency, and here we can have a frequency minus fs by 2 and fs by 2 here. That this fs frequency is known as a sampling frequency. This fs is known as a sampling frequency. We cannot represent any signal which is continuously in nature in a MATLAB, because for continuous signals we require an infinite number of signals. So first what we do, if you have this signal g of t, we will sample the signal. So after sampling, the signal will looks like as this form. This is the samples are taken, and this sample version is known as a g disk of t, and this is represented as a discrete time signals, that is starting from 0 ts 2 ts 3 ts and all. So this ts is known as a sampling interval, and it is uniformly considered. So we have a every times whenever we are taking samples, so we are taking the samples at consecutively the time slots of 0 ts 2 ts 3 ts etc, and the inverse of this one is known as a sampling frequency. This is known as a Fs is known as a 1 by Ts. So 1 by the sampling interval, we can find the another parameters Fs, and that is known as a sampling frequency. So first what we need to define is, now I summarize the step. The first in this experiment, first we define sampling frequency or sampling interval Ts, and sampling frequency Fs. This is the first step. Now in the second step, we will choose two different signal that is the known as a G1 of t and G2 of t. Two different signals we are choosing. Again, we are considering this G1 of t is the sinusoidal signal with some frequency with f1 frequency, and G2 signal is the another sinusoidal signal with some a1 amplitude and f1 frequency, a sinusoidal signal with a2 amplitude and f2 frequency, right? Now the third step, where we take addition of both signal, that is simply defined as a g of t, which is represented as a addition of g1 of t and g2 of t. Very importantly, g of t is the addition of g1 of t and g2 of t. And then finally we take the Fourier transform. We can plot this graph, we can plot this graph also. This the plot g of t with respect to the t. Then we will take the Fourier transform, and for a Fourier transform in a MATLAB, we have a direct command is available, that is known as a FFT. So we take the Fourier transform of signal g of t. right? And then what is available is the g of f. So because every signals in a time domain, if we take the Fourier transform, then we have the signal available in frequency domain is g of f. now we plot now we plot this signal g of f versus the frequency. Plot g of f versus the frequency. Very, very important list that we need to consider here. So again, I repeat the steps what we have considered. The we can consider what we can choose here. We can choose the signal G1 of t. We can choose another signal G2 of t. Before that, we need to find the sampling. We need to decide the sampling interval and as well as the sampling frequency. Then, after choosing the two different signals G1 of t and G2 of t, we produce another signal G of t by simply addition of G1 of t and G2 of t, and this g of t is basically passed through the process of a Fourier transform, and then finally as an output we are able to get the frequency domain version of g of t signal, which is simply known as a g of f signals, and then we are going to plot the graph of g of f versus f. So these are the basic steps are available, and now we will implement. Now the task is that the task next task we are going to perform is implement signal g of f. Implement this experiment, sorry, not this one. Implement uh, experiment using MATLAB simulation toolbox. Simulation toolbox. So now I am disconnect. I am here, but I am now log off from this iPad devices, and then I am connecting with my desktop. So you just wait, and in the desktop we will see how the actual implementation of this experiments will be performed. Okay, so I have joined this, and now we will see the experiment using a LabVIEW. Sorry, MATLAB software, and I'm going to share my screen with you. I think it's audible, right? Once the screen is visible, you just confirm me, so I can say the screen is visible. Yes. Are you able to see the screen in which the MATLAB code has been written? Are you able to see this?
Yes, sir.
Okay. So this code in which what is the experiment today? We want to the experiment is to find the Fourier transform of any signal g of t, what it. Right? This is the experiment. Now, what see if you memorize the steps what I have mentioned earlier, uh, then you may find the first step was is to decide the sampling interval or sampling frequency. So sampling frequency is decided over here, 2 raised to 10 samples in a hertz. It's quite large. Then the second one is define the sampling interval. So sampling interval and the are inversely proposed. So is variable chapter use is equivalent to the P and that not period. Then the how many number of samples we need to consider, because whenever we are going to plot, so we can have some finite number of samples. It's the finite duration signals that we always have to consider whenever we are going to find the Fourier transform. As I have already mentioned, the Fourier transform does exist only for a non-periodic kind of a signals or the signal which has the some finite durations. Into that ones we need to define the how many numbers of total sample does lies within a signal. So that's why we are giving the limit of 2 raised to 20 are the number of samples we are going to consider for the signal. Then now we have a time vector. So time vector is simply considered as from 0 to L minus 1, 0 to L minus 1 multiply with the t. Right. Why we are considering this one? Because 0 to L minus 1 will create a all. Let's create a vector starting from 0 to the L minus 1, and all these are multiplied with the t samples. This is done because it simply means the first sample is 0, then the next number is 1, 1 multiplied with the ts, so second sample is taken in ts time period. Then this vector 0 to L minus 1 will produce a 2, 3, 4, 5 in consecutive sequence. So it means if t is multiplied with all these numbers, it means the first sample is t is multiplied with 0, that is 0. Then the next, it's like this one. This will create a number from 0, 1, 2, 3, like this, right, etc. And the last number is L minus 1, and that is multiplied with the t. So it means the what it will be produced. This t is first multiplied with the 0, so that is the first sample is taken at t. Then the t is multiplied with the 1. It is means 2 ts first 1 0 to ts time period. Then this t is multiplied with the 2, so it means the 2 ts time period, and then 3 ts time period, 4 ts time period, etc. So we are taking the samples at the time interval durations of a ts, and the first sample is taken 0, the next is taken ts time period, the next to next will be taken at a 2 ts time period, 3 ts time period, etc. So create such kind of a long vectors in a time domain for the it's known as a sampling intervals, that we are using this configuration 0 to L minus 1 multiply with the t, and then finally it is assigned to the some different variable is a t. So t is a vector with the total L elements, because we have started from 0. That's why here it is written L minus 1. Actually there are L elements are there, but we are going to starting point is 0, not a 1. If we are starting something from 1, that we go from 1 to L, but we are starting from 0. So that's why to make the count same as L, we are going from 0 to L minus 1. So that way we are going to do this, and that is the T is a time vectors which collect the sampling intervals like as a 0, TH, 2 TH, etc. Okay, now the next the second step. So what is the first step we have to do here? The step number one is very important, is choose sampling interval and frequency sampling frequency. This is the first step. Now we will go to the next step. So next step is step number two. In the step number two, we have to define amplitude and uh, frequency of two different sinusoidal signal, right? So that's why we are using the variables. Step 2.1, I write 2.1. So first we define the amplitude of first signals known as A1, assign some any arbitrary values. Here it is 0.2 is chosen. Now the another signal is our X1 of t signal. The second signal is X2 of t signals. We first choose the amplitude of X1 of t signal as a 0.2. We choose the amplitude of a second signal X2 of t. It is A2 is equal to 1. Then we choose the frequency of the signal. The frequency of the first signal is defined as 100. The frequency of the second signal is defined as 200. Right, so we have defined the amplitude. This two defines the amplitude of consecutively signal number 1 and signal number 2, and this two defines the consecutive frequency of the consecutive signals of x1 of t and x2 of t. Now, next step is basically subcategory of step number 2. So, step number 2, we can say is a 2.2, where produce two different signal x1 and x2, right? We can produce because we have already available the amplitude and frequency of two different signal x1 and x2. So now we can produce the signal and assign to them as a x1. So x1 is a sine omega 0 t, that we know. So a1 times sine omega is 2 pi, so it is 2 pi f1 of t. So it is a1 sine omega 1 t. That is simply defined as x1 of x1 signal is simply defined as a1 times sine omega 1 t, where omega 1 is a 2 pi f. Same way here we define the next signal. So next signal x2 is a2 times sine 2 pi f2 t. F2 is the frequency of a second signal. So here what we can define? We can define this signal x2 with the amplitude a2 and frequency of omega 2, and assume the omega 2 is nothing else but it is the 2 pi f2. It's a frequency in a radians, and if we convert in a frequency hertz, then it is 2 pi f2t. Then we can add this both the signals x1 and x2t, right? And we can assign some different variables to hold this value, and that is why. Now we have to plot the signals in a time domain first. So this figure is actually used, this command is actually used to create a new window for a figure. Then we set the color, which color we like. So here there is a command of a set. You go in a MATLAB help and you find more descript analysis or this more description of this command, how these commands can be used, what is the syntax, and how where it can be used like this with the different colors, styles, and all. So this set is used to define the color. So we have defined the color size. Then we plot the graph of this, but we see we have a number of samples are there. So we are not going to produce all these samples. Otherwise, the signal becomes a too patchy and too cluster and very dense in our in this region. So we are selecting only first a few signals. 100 points are selected and 100 amplitude points are selected. So we will plot the graph of t versus y, right? T versus y. But this t is only 100 points and y is again only 100 points. 1 to 100 means only first 100 points are plotted. And we are multiplying with fs because this is actually a time domain and we are converting as a sampling interval. So the sampling frequency is used for a normalization purpose. This is a discrete version. Now we plot the graph of t versus y. This is the actual signal represented in a time domain, right? and now we can give some title of the signal. X label is the time domain, Y label is the amplitude. So we'll give some time domain label on X label, we give the Y label, title, etc. So these are all these things. Now this first part is complete, right? We can have to produce the signals, then we can have to produce the two different signal, add the signals, right? Step number 3, to produce the different signal X1 and X2, and added them, right? Added them to produce resultant signal and signal Y. That part we have done. Now we came to the next portion, step number 4. So step number 4 is to find, we can say it's a comment line. So step number 4 is find the Fourier transform of the signal. So here we are in a process to find the Fourier transform of the signal. So it's known as a calculate the spectrum. Spectrum, we find the spectrum. So there is a command known as a FFT. It's known as a fast Fourier transform. You can, this command is basically used to convert any discrete time domain signal in a continuous frequency domain signal. So this FFT is used for a discrete time domain signal into discrete frequency domain signal. So this command is used for this purpose. What is the input argument? So input, we have to give the signal which is in time domain. So here we give the Y as the input of this FFT, which is a time domain signals, and then FFT will convert them in a frequency domain version and then assign that as a capital Y. So small y is considered as a G of t signal, time domain version of signals, and capital Y is considered like as a G of f, the frequency domain version of the signal. So we can do this, and this L is basically used to normalize the value as we are using a not a continuous time signal, but we are using a discrete time signal. So very importantly, for any of the discrete time signals, we need to normalize them by L, otherwise the amplitude becomes a large. So to make it down, or to make it in a between a 0 to 1, we normalize with this L. L means all the amplitude does lies within the 0 to 1 now. So that's why we need to normalize this with the value of L, and this process we have to do for any of the discrete time signals. If we are using the continuous time signals, that we don't need to normalize, but if we are talking about the discrete time signal, we need to normalize it. Okay, now we want to plot, but what is the amplitude of this? So here I have discussed, we have a signal g of t, and if we find the Fourier transform of the signal, so that lies from minus fs by 2 to fs by 2, minus fs by 2 to fs by 2, and in between middle point is a 0. So we are getting the half spectrums of the left side, means negative side, minus fs by 2 to 0, and the half spectrum on the right side from 0 to fs by 2. Now in this programs, we are not interested to plot this negative spectrums, negative parts of the spectrums, because the negative parts of the spectrum does lies because of the symmetry in mathematics. But in real sense, if we observe the signal using a spectrum analyzer, so the frequency is not never negative. So we are able to observe only the right side portions or the positive portions of the spectrums, and that's why what we need to, we have to consider only the half a point, not all these points. So this will consider 1 to L by 2 plus 1. Plus 1 is added because 0 is considered, right? 0 is considered. So there is extra points we are considering to accumulate the 0. Otherwise, we are considering only the portions from 0 to fs by 2. From minus fs by 2 to 0, that parts we are not going to consider. So that's why only half points are there, and whenever we are finding FFT of any signal, so that will represent the signal amplitude with frequency. So that is always a complex, and MATLAB is not able to plot anything which is in a complex. So to convert the complex value to the real value, we are using absolute. Absolute will convert anything which is imaginary or complex into the real part. For an example, if you have a signal x plus jy, and if we find the absolute value of x plus jy, so it is square root of x square plus y square. So if anything which is in a complex or imaginary form, by using this command abs, means absolute value, we are able to convert in a real portion only. And if we are considering only the half spectrum 0 to fs by 2, and we are only fs by 2, so to make this so it means the energy is double, right? Energy is now double because we are considering half person, not another half person. So that's why the 2 is multiplied, that's energy is double. We are adding them, so we are considering only 2, so they have a double energy. And then this fs by 2. Okay, so frequency spectrums are plotted. For this one, amplitude points are already taken in the earlier amplitude of y. They have a 0 to fs by, they have a L by 2 plus 1 points are there for amplitudes. Now we have to present the things in a frequency domain. So frequency are also considered from 0 to 1. Line space 0 to 1 means the points from 0 to 1. How many points we are going to consider between 0 to 1? L by 2 plus 1. And all have been assigned multiply with the fs by 2. It means the first point is a 0 multiply with the fs by 2, it is 0, and the last point is also multiply with fs by 2. It means our frequency domain here f is starting from 0, then some value of, let's say, 0.1 to fs, then 0.2 to fs, like this up to the last element is L by 2 plus 1, right? L by 2 plus 1, and that is sorry, this is multiplied by fs by 2, fs by 2, this is multiplied by fs by 2 till the last point. Last point is L by 2 plus 1 multiplied with the fs by 2. So we are creating this x-axis for a frequency domain, and this frequency ranging, the range of this frequency is starting from 0 to fs by 2. And if we are choosing the two different signals, so they have a consecutive frequency at f1 and f2, we want to go from f2 frequency. So this L by fs is actually used to define how many sampling point is equal to one frequency. So that is normalized, the total number of points is normalized by the sampling frequency, and that is multiplied with the maximum of f1 and f2. Which one is maximum? We want to plot the signal up to that only, f2 frequency only if it is maximum, f1 frequency only if it is maximum. So that defines which is the maximum frequency, and plus 1 is basically because 0 is considered. So we have a f frequency domain vector is available. We have amplitude vector is available, amplitude wise. So we have two different vector, one to represent the frequency on x-axis, one to represent the amplitude on y-axis, and then finally we are going to plot the signal figure, then set, and all this are to plot the graph. Only I points, only first I point we are interested to display, and this I can be calculated by this one. Then this set is actually defines the box and color. Title is give the labeling, x label and y labels are give to gives the labeling on x axis as well as on the y axis. So this is the complete picture. Now you see how much which frequency we have used. So we have used the two frequency 100 and 200. But whenever we are combining the signal y is equal to x1 plus x2, so in signal y we are not able to identify the two different frequency component. But whenever we are able to, whenever we are doing the Fourier transform and we observe the signals with respect to the frequency or frequency spectrum of signals, so we can easily separate these two different frequency, 100 Hertz and 200 Hertz. So now I run this code. After running this code, you can see this is the time domain version of the signals. It's too clumsy because there are multiple components are there, so they are added in so sparse that you are not able to see this one. But if you see, if we sorry, yeah, if you see this one, are you able to see this graph? Figure number 3. Are you able to see the frequency domain version of the signal? Are you? Hello? Hello? Are you able to check the frequency domain of the?
Yes, sir.
So you see, yeah. So in x-axis we have a frequency, and on y-axis we have a amplitude, y of absolute value of amplitude. So that is normalized from 0 to 1, and that's why L is divided from all this value. And on this one, on x-axis, you find the frequency. So you here we have a two components. F1 signal with F1 frequency is of 100 hertz, and the second signal x2 signal with F2 frequency, which is approximately 200 hertz. So x1 signal with 100 hertz frequency and the amplitude is 0.2 A1. The second signal with the amplitude of 1, A2 is, we have selected A2 is equal to 1, and that is of frequency F2, which is of 200 hertz. So you see there are two frequency components that lies in your signal. One is located at 100 hertz frequency, second is located with a 200 hertz frequency. The first signal which is located at 100 hertz frequency, they have an amplitude of 0.2. The second signal which is located at a 200 hertz, so they have an amplitude of 1. So from this one you can easily separate out the number of frequency components your signals. That pictures cannot be highlighted during a time domain signals. In time domain versions, you are totally remains a blank about how many frequency components are involved in your signals. But if you convert them in a frequency domains, you can easily separate out those frequency component, and you can see you can clearly visualize how many frequency component does lies in your signal. So that graph will show everything. And one more thing that I need to highlight is that the amplitude you can even find, and you can even do the some bandwidth analysis, how much bandwidth is there. So we have a two frequency components are there, 100 to 200 hertz. So total bandwidth of signal is F2 minus F1, 200 minus 100 hertz. It means the bandwidth is 100 hertz. So 100 hertz is the bandwidth of any signal. So that you can identify. So this graph is actually useful to understand the frequency concentrations of the to produce your signal, and along with this amplitude. So individually you can identify which frequency component has a more contributions to produce your signals and which has a less contributions of signals, and you can even find how they are scattered around. You can find the scatter diagrams of this frequency component, so you can identify individual frequency component with that magnitudes, and you can even find the bandwidth analysis using this. That is very important for you. So now this is all for today, and now we are going to came back to the main screen where I would like to take your presence. So you just hold this one. I just take your presence. Okay, so I have already taken your presence, and now we are just disconnected this one. So we stop this recording and disconnect with this